Any questions, doubts from the previous lecture?
सर एक डाउट है सर.
हाँ. Yes, yes.
सर फॉर्क सिस्टम कॉल से एक डाउट है सर. जैसे सर उसमें जब चाइल्ड प्रोसेस फॉर्क रेट को कॉल करता था सर, तो EIP जैसे EIP सेट हो जाता था फॉर्क रेट पे, तो फिर सर अगर मेरे प्रोग्राम में जैसे उस फॉर्क के बाद अगर प्रिंट हेलो लेट सपोज लिखा हुआ है, तो सर फिर वो मतलब वो प्रोग्राम फिर कैसे आया सर, वो हेलो कैसे प्रिंट हुआ सर, क्योंकि फिर तो ट्रैप रेट वहां से कॉल हो जाएगा सर जब फॉर्क रेट रिटर्न करेगा. और
फिर से बोलो.
जैसे सर जैसे मेरा चाइल्ड प्रोसेस जब एग्जीक्यूट होगा तो EIP it's set to fork rate. Now when fork rate returns, then trap rate will be on the top of stack. Then my program sir like fork के बाद जो मान लीजिए printf hello लिखा हुआ होगा, फिर वो सब कैसे कहाँ गया सर, वो मतलब समझ में नहीं आया सर.
एक दिन और थोड़ा ट्राई करो, मेरा क्लास वीडियो ढंग से देखो, ठीक है?
ओके सर.
You will be getting the answer. मैंने कई बार उसको फोर्स किया था. Pay attention on this point. Why fork rate is there? What is the use of fork rate? Okay.
Yes sir. Yes sir. I will watch it.
Okay.
Okay sir. I will watch it.
Any other question? I can tell you right now, but I want you to figure it out by yourself. Okay.
Okay sir. I will try.
Yes. Any other question? Okay, if there are no questions, yes. Any question?
Yes sir, last time आपसे पूछा था वो P2 स्टैक में क्यों जंप करेगा, P1 के स्टैक में क्यों नहीं, जब एड्रेस सेम है दोनों में.
बताया तो था आंसर.
सर आंसर नहीं बताया, आपने बोला क्लास वापस सुनने के लिए. उसमें स्विच UVM और स्विच KVM ऐसे कुछ थे, मतलब कि
कर्नल वर्चुअल मेमोरी, और वो अभी पढ़ाएंगे, ठीक है? जब वर्चुअल मेमोरी देखेंगे, मेमोरी मैनेजमेंट, वहां अभी मत फंसो. सिंपल सी बात ये है कि उसके बाद मैंने तुमसे कुछ एक्सरसाइज भी कराई थी वर्चुअल मेमोरी वाली, ठीक है? ध्यान है?
हाँ सर याद है.
एड्रेस स्पेस ट्रांसलेशन, रैंडमाइजेशन, ठीक है? सो जनरली क्या है कि वर्चुअल एड्रेस भी अलग अलग होगा, ठीक? तो स्टैक तुमको आराम से मिल जाएगा, क्योंकि स्टैक तुमको किधर चाहिए, तुमको चाइल्ड का स्टैक चाहिए, तो चाइल्ड के स्टैक में प्रोग्राम काउंटर चला जाएगा. यू विल बी एबल टू हैव दैट थिंग. Fine. But there is a role of kernel virtual memory and the switching to the kernel virtual memory also. We'll be coming to that point. Okay. Right now, don't get confused. Right now, just think that if child want to execute or any other process wants to execute, you need to switch from the user stack to the kernel stack first of all of the existing process, and then from the kernel stack to the kernel stack of another process. Are you getting the point? And obviously the kernel stack address. Yes.
Yes sir, कुछ नहीं. Yes sir कह रहा था.
Okay. So your confusion is if the virtual addresses are same, how the things are going to be clear. Look, even if the virtual addresses are same, their mappings would be different. There would be different tags, because that virtual address space is part of another process image. So there would be certain other things which will make it part of another process. Fine. So let's not confuse with this thing कि अगर same address, पहली बात तो होता नहीं है same address. So you may be a big process, another may be a small process. Fine. So kernel stack might be in some different area. So let's not get confused regarding that. Just tell me one thing, whether you are clear about how the switching is happening. Whether the address is same or not, that's a different story.
Yes sir, that part is clear.
So then it's okay. You'll be clear after some time. Okay. Yes.
Sir.
Any other doubt? Okay, if there are no doubt, then we can start the lecture. I'll just take 1 hour class, one 1 hour 15-minute class, but this is an important class, and that's why I'll teach for only like 75 minutes or so, because you need to understand all the things very clearly, because the systems you are using are following these kind of scheduling policies. As we have already seen, uh, XV6 scheduling policy was very simple. It's a Strawman scheduler over there, where the processes are organized in P table, and these processes or proc structures are there in a P table. So you just go through the P table and find out first runnable process. Pick the first one which is runnable, and whatever you are suspending, whatever task is running or process is running, you will be putting it to the end of the list. And it's a kind of round robin scheduling which is getting implemented in XV6. So you take the process which is runnable, which is ready to run, not waiting for any event to happen. If a timer interrupt comes, you go and see the runnable process, put the running process at the end of the list, pick the first runnable process, schedule it, make that state from runnable to running, and then switch to the scheduler and the things which we have already seen. So it's a only round robin scheduling policy, which is far from ideal. There has to be incorporation of priorities also, that because here you are doing a simple search, only you are choosing a runnable process. If there are 5 or 6 or 20 runnable processes, then you are not paying any attention. You are just moving through the list. The first runnable process you are getting, you are picking it up, scheduling it, and running process you are keeping it at the end of the list. It's a very simple Strawman policy. But in real systems, in real operating system, bigger operating system, complex operating system, you require more than this. And that's what we are going to see. We will grow this lecture slowly and gradually, and finally we'll be reaching to the Linux scheduling techniques, that how in Linux things are happening. That's what is the today's agenda. So one thing is sure, that we need some kind of priority-based scheduling, because not all processes are equal. Now, if the process is compute intensive, means it is needing CPU for more time. It is CPU bound process. So obviously you need to give it to a lower priority, because it will take more time of its execution, the total lifetime, more time it will take for executing on CPU. Obviously you have to give higher priority to the interactive processes, interactive process where user is interacting. So user is needing CPU for a very small time, and then it goes for the IO. Then again, very small time goes for the IO. So this mouse clicking, the keyboard command firing, all these are IO activities, which are slowest one. But to make the things interactive, for interactive, you can't keep the user waiting. That okay, I have given the command, but the command is not able to execute on the CPU because any other process was executing. So for interactive process, you need to keep priority higher. As and when the interactive process is needing the CPU, it has to be given to that. So we need some sort of priority-based scheduling. And how it can be implemented, simple way is each process is going to be assigned a priority. And then you will pick the process in ready queue which is having the highest priority. So it's not as simple as it is looking like, because if you solve one thing, it will lead to another problem. It's okay that you can assign priorities to the process based on their nature, whether they are CPU bound or IO bound. And interactive process, you can give highest priority. The batch processes, you can give the lowest priority. That's okay. And then you, using this priority, you can have a have your scheduling mechanism or scheduling algorithm. But there are some downside also. Advantages is clear that you will provide relative importance to the processes which are having higher priorities. But the disadvantage is dangerous. So you may not be reaching to a point where some lower priority processes are starving and they are not able to get the CPU at all. Because if you keep on catering for higher priority process and these higher priority processes keep on coming, then the lowest priority process or lower priority process will not be able to get the CPU. So there would be a chance of starvation. So it's true that we need some sort of priority-based scheduling to provide better response time. This is a design issue also for any operating system design, that you should be giving a better response time. But the downside is that you should not be leading to a situation where some process which are apparently having lower priority are getting starved. So on this particular premises, the whole discussion is going to be there, that how we can have a priority based scheduling is still we will be trying to avoid the starvation of lower priority process. This is what is going to be the premises of today's discussion. Fine. Priorities that can be set internally by scheduler or externally by users. Priorities can be dynamic or static. When we talk about a static priority, these are the priorities which are fixed. So once the priority is given to a process, that process would be having the same priority up till its end of life. Dynamic priority, scheduler can change the priority during execution to achieve scheduling goals. Scheduler can decrease the priority of process to give another process a chance to execute. Or scheduler can increase the priority of IO bound process to provide better response time. So all type of combinations are possible, and actually all are used in a real general purpose operating system like Linux and Windows. So priorities can be set internally by scheduler, or users can also assign the priority or change the priority. Priorities can be dynamic or static. Static priority where priority of process is fixed. Dynamic, it can be changed by scheduler depending upon the need. So all these kind of possibilities are going to be there. Starvation. Scheduler adjusts the priority of process to ensure that all should eventually execute. There are several techniques possible, and some of the techniques are going to be utilized in real operating systems also. The major issue here is to avoid starvation. Now, one of the technique can be that every process can be given a base priority, and after every time slot, increment the priority of all other process. Suppose process P1 is executing, and after P1 has executed one time slot, so apart from P1, the priority of other processes are going to be increased, so that before P1 can execute next, another process can get chance. And slowly and gradually, this will ensure that even a lower priority process will eventually execute. Suppose all processes are getting chance and a lower priority process, so slowly and gradually the priority of lower priority process is also increasing, and eventually it will also get chance to execute. So this is one very basic technique that give a base priority with all the process. That process which is able to execute will be having one priority, and after one time quanta, the process which was executing is going to come out of CPU, but at that point of time, all other process would be having some increment in their priorities, so that before P1 gets chance, another process can get chance. But there is an issue here. If you have priority scheduling with larger number of processes, so as you know that all the several processes may get assigned same base priority. So, so this will eventually end up behaving more like round robin scheduling. So I'm just giving you an idea that how different techniques can be applied to avoid this problem of starvation. So we started with one, uh, you can say one admission that priorities are necessary because processes are not equal. They are having different nature and behavior. So we will have, will have to have uh, variations and variable priority levels. But at the same time, we need to avoid the starvation and we need to apply techniques for that. This is what we are going to see today. So the first typical example is multi-level queue. Now, instead of having single ready queue, we'll be having multiple ready queue. And different processes would be categorized into different priority class. So as you can see in this figure that real time is the highest priority real time process or interactive process. Then the real time process where they need to be finished within a deadline. System process, operating system's own process, interactive process, and then finally the batch process. So here the lowest queue is having the lowest priority and highest queue is having the highest priority. Now what would you do instead of having a single ready queue? You will be dividing your queue into various different queue depending upon their priority classes. What scheduler will do? Scheduler will check the highest priority queue, and if there is any process there, it will be scheduled first. Now, if there are no process in the highest priority queue, it will go back to the lowest priority queue, lower priority queue, then lower priority queue, then so on and so forth. Now, within a queue, any scheduling policies can be used. Any of the scheduling policies can be used. Typically, it is round robin that within a queue, suppose there are 4 or 5 processes in any queue, then how would you choose and what would the scheduling policy among these processes in same class? That is typically round robin, but we can implement another scheduling policies also. Now, even if this is apparently a good idea, but there is an issue. If suppose real-time processes are continuously arriving, what will happen? Scheduler will always pick a process from the highest priority queue, and lower priority queue may starve. So we need to think about something else, and that's what we're going to see in the next attempt. Scheduler can adjust time slices based on the queue. IO bound process can be assigned to higher priority with a larger time slice so that they can be finished. They can finish their CPU burst in that time slice. So what you can do, you can assign bigger time slice, time quanta to highest priority process just to ensure that their CPU burst can be finished in this time slice. CPU bound process can be assigned to lower priority with shorter time slices because again and again they are going to run on CPU. They are not going to cater for the IO interrupt that okay, IO is completed, you need to do the IO thing. This can be done. Scheduler can adjust time slice based on the queue, but the problem is again same. If there are processes in higher priority queue, lower priority queue will not get chance to execute. Disadvantage class of a process must be assigned a priority. This is the another problem. that you should be knowing the class of a process before it starts execution. How can you know whether it's a real-time process or IO process or any other process? You can have a guess. You can think of, many people can say that we can apply machine learning or do some prediction or something like that. But to solve one thing, you would be executing a lot of code. So this is not the most efficient way, because you need to know the class of process a priori. That is one of the issue. And then starvation is also possible. So what is the next attempt? That is multi-level feedback queue. So what they are trying to do, they are trying to think in a different manner. There would be a higher priority queue at the top with a shorter time slice. If it's a higher priority queue with a shorter time slice. If it finishes its time slice, it is likely CPU bound. Means if it is finishing its time slice, but CPU burst is not over. Every process will go into the highest priority queue. So every process will be scheduled once. If time slice is over, but CPU burst is not over, that process would be demoted to the next queue. If time slice is over and CPU burst is also over, it means it is actually a higher priority process, because it can finish its CPU burst in that shorter time quantum. So the process which is having larger CPU burst will move down. Here also it will get a chance to execute. Again, if CPU burst is remaining, it will be, when it is preempted, it will be moved down. Preempted, move down. In this way, you are ensuring to give chance to all the process. But what will the issue here? The issue here is, once a process is at the lowest level, again you will come back to this situation. Okay, it got chance. It is not a straightforward thrown to this queue. It is started from the highest queue, highest priority queue. But eventually there would be processes in the last queue, last priority queue, and these processes will be starving. So these are the different attempts which are during the evolution of scheduling policy. These attempts have been made. Multi-level queue and multi-level feedback queue, with one design issue is in mind, that you should give higher priority to the interactive real-time process, but no process should starve. Here we have seen that in both of these techniques, starvation is possible, whether it is multi-level queue or whether it is multi-level feedback queue. Now, what is happening in Linux? That's the question. In Linux, there are two types of process. First of all, there is a coarse-grained categorization. Divide all the process into two big classes. Real-time process, where deadlines must be met. It should never be blocked by a lower priority process. And normal process. Normal process can be either interactive or batch process. Interactive process would be IO based and batch process would be CPU bound. So first of all, Linux divides process class, two process classes, normal process and real-time process. Real-time scheduling is handled in a different manner, and normal process scheduling handled in a different manner. The scheduling in Linux is modular. Different types of process can use different scheduling algorithm. So it's not like that there is one scheduling algorithm which is getting utilized by all the process. Depending upon the nature of the process, the class of the process, different process can use different scheduling algorithms. If you go by the scheduling history of Linux, up till 2.4 to 2.6, we used to use ON scheduler. Then for many years, 2.6 to 2.6.22, ON scheduler and ON scheduler worked. You can see we are up to 2.6.22. Here, ON and ON scheduler were working. But finally, they realized that these two scheduling policies or scheduler technologies are not helpful. Then we switched towards complete fair scheduler, CFS scheduler, and Linux 2.6.23 onwards, the CFS scheduler is in place. What is ON scheduler? At every context switch, scan the list of runnable process, compute the priorities. How to compute the priorities will be coming to that. Select the best process to run. And as you can see, because you need to scan the list of runnable processes, then you need to compute the priorities. Fine. So a complexity of this particular scheduling would be order of n if there are n number of runnable process. Just a minute, I have to take this call. Sorry. So as you can see that because if there are n number of runnable processes, complexity would be order of n, and this is not scalable. When Java was introduced, these scalability issues were observed because Java virtual machine, which is running over Linux, can spawn many threads. Threads, what are threads? We'll see later on. These are lightweight process. So Java is Java virtual machine works over the concept of multi-threading. So it can create many threads, and suddenly the number of threads would be increased. So then the scalability issue was observed when Java was introduced. So order of n scheduler was not very successful. It was successful for some days, for few years rather, but they need to switch towards O1 scheduler, means constant time schedule. Fine. Now, what was O1 scheduler? Constant time required to pick the next process to execute, which can easily scale to large number of processes. As I told you, processes are divided into two types. Real time, will see the real time scheduling, where priorities are from 0 to 99, where 0 is the highest and 99 is the lowest. Then the normal process, which includes IO bound and CPU bound both, and priorities ranging from 100 to 139. 100 highest and 139 lowest priority. So this is a constant time scheduler. How it works, let's see. There would be two ready queues in each CPU. And I'm talking about the normal process from 100 to 139. And each queue is going to have 40 priority classes, 100 to 139, where 100 is highest priority and 139 has lowest priority. And these two queues are designated as active run queues and expired run queues. What is the meaning of these? I'll tell you. If you see it carefully, it is looking like a hash table. Or you can say it's looking like a graph, data structure, adjacency list, if you see carefully. So two run queues, for every priority level a different queue. Two run queue, one is designated as active run queue, another is designated as expired run queue. What is going to happen? Pick first task from lowest numbered queue. And this is a constant time. You can have a hash table, hash map, fine, any type of thing. Pick the first task. I'm not saying which task of this queue. Pick the first task from the lowest number queue, execute it, and then throw it back to the expired queue. Put the task in appropriate queue, which is expired queue. So after executing once and if it is not finished, the task will be transferred to the expired queue. So slowly and gradually what will happen? All the tasks, all the process of this active run queue will be handled, and after executing once, they will be transferred to the expired run queue. After some time, there will be no task in the active run queue. Then make this expired run queue as active run queue and create another empty expired run queue. Once active queues are complete, make expired run queue active and vice versa. So they're saying it's a kind of feedback happening. So you run it from one queue, shift it to expired queue, another first task, keep on doing it till all the active run queues are done. Then make the expired, and up till this time there would be process in the expired run queue, make expired run queue active, and there would be another expired run queue. In this way, O1 scheduler works. There are two steps in scheduling, as you say. First of all, find the lowest number queue with at least one task. And then the second step is choose the first task from that queue. Step 2 is obviously constant time. Choosing the first task from that queue is constant time. Now the question here is the step 1 constant time, where you are finding the lowest number queue with at least one task? It may so happen that you need to scan it from here to here to here to here to here, and you are looking for a queue which is having at least one task. So whether this is step 2 is constant time, or sorry, step 1 is constant time or not, where you are finding the lowest number queue with at least one task, trying to find that. So what is happening in Linux? And there is a special instruction in Intel based machines. Find first bit set, BSFL, on Intel based machine, which is storing bitmap of queue with non-zero entries. So if you remember your data structure classes, we can store a graph data structure in two manners. One is adjacency list, where you have a different link, an array, and an array of different linked list. This is a graph adjacency list data structure. Another way of storing a graph is to store in an adjacency matrix, where if there is an edge, there would be 1, otherwise there would be 0. Any other arrangement you can have depending upon how you are interpreting that. So similarly, we can have a bitmap of queues with non-zero entries, and then you'd be using this special instruction, find first bit set, BSFL on Intel, to get to the lowest priority queue with at least one task active. So I'm not spending my time here. I'm giving this as a reading assignment, that how this BSFL work and how it is helping to make this first step constant time. This is for you to read by yourself. Priorities. As I told you, 0 to 99 is meant for real-time processes. 100 is the highest priority for a normal process, and 139 is the lowest priority. So I'm not right now talking about real-time process. So our focus right now is normal process, where 100 is the highest priority for the normal process and 139 is the lowest priority. So we are dealing with both type of priorities, static and dynamic. So when a process gets created, a base priority 120 is assigned. 120 base priority is assigned. There is a nice command whose name is nice only to change the default priority of process. You can write this command on Linux box and you can change the default priority of the process with some nice values. If you give 119 plus 19 to the nice command to a process, so what you are trying to do, you are getting generous that I will go last. I'm reducing my priority. I'm lowering down my priority. If you give minus 20 to the nice value, you would be moving towards the highest priority that I want to go first. So new process will be assigned a 120 priority, base priority. You can use nice command to change the default priority of a process by giving nice values that how much you want to change it. So this is how static priorities are working. But there is a dynamic priority also. It is used to distinguish between IO and CPU bound process. And this is based on some heuristic. And the heuristic is very simple. If there is a IO bound process, it will sleep more because it is waiting for IO to happen, and IO is slowest. And if it is the IO bound process which is sleeping more, then make that IO bound process higher priority. A CPU bound process will sleep less because it is not going for IO interrupt. It is not waiting for any IO. It will sleep less and it should get lower priority. So based on the average sleeping time, some bonus values are fixed. And how to calculate the dynamic priority? It would be max of 100, min of static priority minus bonus plus 5, 139. So what you will be doing, even if you make your priority process highest priority, suppose Linux will give 120, you give nice value minus 20, and you are thinking your priority would be the highest priority. No. What will happen? Then this dynamic priority heuristic will be applied. So whatever is your static priority, say 120 minus 20, 100, depending upon whether you are sleeping for how much time, the bonus will be taken, then plus 5, and then minimum of these two value, and then the maximum of 100 and this, and then finally your priority will be calculated. So this is how dynamic priorities which are based on heuristics are calculated. Dynamic priority determines which queue to put the task. No matter how nice one is still need to wait on run queues, and that prevents starvation. Otherwise, user can keep on giving priorities 100, 100, 100. So all the process will be chosen from the lowest priority only. So that will not go. That is not going to happen because you need to calculate the dynamic priority by this heuristic formula. So in this way, you can prevent the starvation. Time slices. As you know, IO bound interactive process have high priorities. but they are likely to not complete their time slice. Give them the largest time slice so that they can complete their CPU burst without being preempted. So there is again some heuristic here. If priority is less than 120, then the time slice would be calculated by this formula, 140 minus priority into 20 millisecond. Else, if priority is more than 120, then time slice would be 140 minus priority into 5 milliseconds. These are some heuristics which are just trying to suggest that if it is an IO bound process, give it enough time so that it can complete its CPU burst in one go before being preempted. And if you can see here, static priority, then the niceness, and if you put everything here in dynamic priority formula, and then in time slice formula, you will be getting the time quanta of 800 millisecond. And if the priority is lowest, 139, and then the time quanta will be 5 millisecond. So it is dependent upon two things. One is what is the priority given by system, then what is the niceness given by user. Depending upon that, system will calculate the dynamic priority, and depending upon that dynamic priority and the value of that dynamic priority, the time slices are calculated. In this way, it is trying to balance out everything. Summary of O1 scheduler is a multi-level feedback queue with 40 priority classes. Base priority is set to 120 by default, which is modifiable by users using nice command. Dynamic priority is set by heuristic based on sleep time. And time slice interval is set based on the dynamic priority. Limitations. Actually, it is complex heuristic to distinguish between interactive and non-interactive process. There is a dependence between time slice and priority. So priority is dependent upon dynamic priority, and dynamic priority is dependent upon the sleep time, average sleep time. And then finally, the time slice is again dependent upon the dynamic priority. So there is a lot of dependence. And that results in priority and time slice values non-uniform during the execution of system. Fine. So this is about ON and O1 scheduler. Fine. I'm not going to start the actual scheduler which is getting used by Linux since 2.6.23. This I will start in the next lecture. This is incorporated in Linux kernel since 2007, and these are based on rotating staircase deadline scheduler RSDL by Con Colivas. There are no heuristics in CFS, but it is very difficult to comprehend and understand. So I just want to give you some time to think over it. Think over ON and ON scheduler. Read something more if you want, and try to use this nice command by yourself and see. Try to do it, do your assignment of XV6 where nice is investigated. Please do it by yourself, and then on the next turn I will start the CFS, the complete fair scheduling policy of Linux, which is getting utilized nowadays. Any questions from anybody?
Sir, can you open the slide about the ON scheduler?
Okay. This one?
Sir, one more. So sorry, sir, it was in O1 scheduler.
Okay. This one?
Yeah. No,
This?
sir, I don't remember, sir. It was inside. I think ON only. Sir, in that you were
What do you
saying
want
that,
to ask? Just tell, ask
sir,
the
that
question.
diagram, sir, that diagram, I don't remember in which slide it was. Sir,
This
in
one.
that it was, uh,
Okay,
sir,
ask
it was,
the question.
yes, sir. So it was like that. If we had to uh, given the priority,
Mm-hmm.
once we, sorry, sir, this was not the diagram. I was having doubt about. I think it was in back.
I'm just moving it.
No,
I'm
sir,
moving
back. Yes,
this one.
yes, sir. Multi-level feedback.
Hmm.
So in this one, you were saying that if the P9 is having more priority, and
Mm-hmm.
so once it does not finish its slice, so it will move to a lower level, the P9.
Yeah, because we have started every process thinking they are highest priority process.
Yes,
Fine.
sir. So,
If they
but
are,
yeah,
let me complete.
yes,
Suppose all these are considered as highest priority process. Fine. So everybody will get the CPU with same priority, maybe round robin. Okay. Okay. Suppose P naught got the CPU, but P naught was not able to finish its CPU burst. All process should start in the highest priority. एग्जीक्यूट कर दिया, चलने लगा, ठीक है। अगर इंटरैक्टिव होता, आईओ बाउंड होता, तो खत्म हो जाता। नहीं खत्म हुआ, तो यानी यार ये थोड़ा और ज्यादा टाइम सीपीयू पे लेगा, ठीक है। उसको नीचे कर दिया, यहाँ फिर एग्जीक्यूट किया, फिर भी नहीं खत्म हुआ उसका सीपीयू बेस्ट, यार ये ज्यादा टाइम ले रहा है, उसको और नीचे कर दिया, ठीक। सो द heuristic here is if a process requires more CPU, then रिस्पॉन्स टाइम अच्छा हो ये जरूरी नहीं है, इसकी जरूरत नहीं है, ठीक है। अगर प्रोसेस को ज्यादा, जैसे हमारे कुछ बैकग्राउंड प्रोसेस हम बोलते हैं ना, चलती रहती है पीछे, जब उनको मौका लगेगा, जब कुछ काम नहीं होगा तब वो चलेगी, ठीक है। अगर वो ज्यादा सीपीयू चाहता है, इसका मतलब रिस्पॉन्स टाइम की बहुत ज्यादा प्रॉब्लम नहीं है, क्योंकि वो सीपीयू पे काफी देर तक चलेगा, उसका इंटरैक्शन बहुत देर में होने वाला है यूजर से। हम लोग जो सिस्टम बनाते हैं आजकल, क्योंकि ऑपरेटिंग सिस्टम इंटरैक्टिव बनता है, कि कमांड लाइन होता है या जीयूआई होता है, तो हमारा टारगेट क्या है कि हाईएस्ट प्रायोरिटी प्रोसेस एक रियल टाइम प्रोसेस हो गई, जो जिसमें डेडलाइन शेड्यूलिंग होती है। हम लोग अभी आएंगे वापस रियल टाइम शेड्यूलिंग पे, ओके, डोंट वरी। बट नॉर्मल प्रोसेस में पहले तो हमको ये डिसाइड करना है यार ये सीपीयू बाउंड है कि आईओ बाउंड है। अगर आईओ बाउंड प्रोसेस है यानी सीपीयू पे कम टाइम चलेगी ना। आईओ बाउंड जनरली होती कौन सी प्रोसेस है जिसमें आईओ इंटरवेंशन होता है, कीबोर्ड का, माउस का और ऑल, यानी इंटरैक्टिव होती है। तो इंटरैक्टिव है, क्यों है? क्योंकि सीपीयू पे थोड़ी देर चल रही है, आईओ पे ज्यादा चल रही है, आईओ बाउंड है। इंटरैक्टिव है, तो रिस्पॉन्स टाइम का प्रॉब्लम है, इशू है, तो उसको हाईएस्ट प्रायोरिटी पे रखेंगे। आप डबल क्लिक करो किसी चीज पे, सीपीयू सब काम छोड़ेगा, पहले आपने जो डबल क्लिक किया है उसको ओपन करेगा। आप लिनक्स पे कमांड चलाओ, आपको सब काम छोड़ेगा और पहले आपको कमांड का आउटपुट देगा। आर यू गेटिंग माय पॉइंट अभिज्ञान?
yes, sir.
Okay, so this was the funda here. Any other question? Okay, so there is an information which I want to share, because in this lab, the previous lab on Wednesday, the task was big. There were two kind of tasks. One was related to changing the priority of a process, and other task was scheduling. So I'm giving you one lab free. Fine. on Wednesday, the coming lab, there would be no new assignment given. So I'm giving you time to complete all the work, pending work. So next lab, there is no foundation if you want to join or not. Fine. If you want to join, next lab means day after tomorrow, you can join if there are any question. Otherwise, there would be no foundation in joining. But I would be uploading the assignment today. So you have to complete the assignment of these two labs, means one lab which has been done and one lab which I'm making it free to join or not. These two lab assignment should be completed before the next lab. Okay, that's what is the information. Okay, if there are no questions anymore, then you can leave. Thank you.